Astrophysics, the study of our universe, can feel detached from our lives here on Earth. But it doesn't need to be. Here in Potsdam, we've recently hosted a large conference with researchers from around the globe. In the process, we've asked some experts to break down key astrophysical concepts, from galaxies to cosmology. In this first episode, we'll meet Dr. Michelle Collins. She'll be talking about dwarf galaxies, some of the smallest and most abundant galaxies in our universe.
So I'm Dr. Michelle Collins, and currently I am a senior lecturer at the University of Surrey in the UK. My speciality is studying dwarf galaxies. So these are the smallest galaxies we can see in the universe, and I focus on those that are quite nearby and try and understand by measuring their stars, seeing how the stars are moving, trying to understand what that tells us about dark matter, and what also we can learn about how galaxies form, especially in the very early universe, because these stars are typically very old in these galaxies. Dwarf galaxies are basically just small galaxies, and the exact definition of what is a dwarf galaxy versus not a dwarf galaxy is somewhat flexible, but it's based on essentially the total number of stars that you can see, so purely based on how much light a galaxy is outputting. So a galaxy like the Milky Way or Andromeda we would call a normal spiral galaxy. And as you go sort of a factor of 10 or 100 lower in mass, then you're sort of, in terms of amount of stars, then you're talking about dwarf galaxies. But then they can go all the way down from sort of hundreds of billions of stars for massive galaxies to the faintest dwarf galaxies, which maybe only have of order a few thousand stars. So it's a huge difference in terms of how many stars there are in the galaxy. I think dwarf galaxies are really interesting because they're this really curious object, and I think extremely useful as well for trying to learn about some of the biggest questions we have. So despite being some of the smallest things we can find, they address really large-scale questions like, what is dark matter? How do galaxies form and evolve over time? What is the smallest galaxy we can form? All of these big questions we think we can address by studying dwarf galaxies. And that's because even though they have very few stars, they're very sensitive essentially to different types of physics. So if you change the nature of dark matter slightly, you'll change the properties of dwarf galaxies quite significantly. If you change the way that star formation happens in a massive galaxy, you might not find that makes a big difference to how the stars form over a Hubble time, so over the age of the universe. But if you change the way star formation happens in a small galaxy, it's the difference between it forming loads of stars and almost none. So they're really sensitive to small changes in physics, and that's, to me, why they're really interesting. We've known about dwarf galaxies for a really long time, certainly some of them, the brighter ones anyway. So for, as long as we have records of the sky, people have known about things like the Large and Small Magellanic Cloud, which are technically dwarf galaxies. But it took longer for us to study and find many of these dwarf galaxies and fainter ones nearby. So I'm not entirely sure what the history is of some of the faintest ones, but in terms of, or some of the intermediate ones have been known about for a very long time. But recently we've had sort of a renewal of interest in the field, sort of stretching back to the beginning of the century really, when we were able to find suddenly much fainter dwarf galaxies than we'd ever found before. So this goes back to the early 2000s with new surveys like the Sloan Digital Sky Survey, which for the first time sort of we're able to do these wide field surveys to quite faint objects and find these really, really faint galaxies nearby. And we found out there was loads of them nearby as well. So that's kind of the first detection of these ultra faints, we call them. And we think these are really interesting dwarf galaxies because they're probably amongst the first galaxies to form. Because they're so small, they probably haven't been able to sustain star formation for a long time, so they would have formed all their stars quite early on in the universe, and now they're kind of like the fossils of the first galaxies. And so understanding how they formed and what they're doing now is really interesting in terms of learning about how galaxies evolve. We have a number of theories about how dwarf galaxies form. And in general, kind of, they sort of cover the same basis. So we think they form very early in the universe, and because they live in these they're very sort of low mass systems, they probably form a bunch of stars quite early on, and then that star formation or other processes in the universe, so external radiation sort of heating up all the gas in these systems, means that they switch off their star formation really early. And then depending on your dark matter model and your star formation physics will change, exactly at what mass scales these things kind of can continue forming stars or not. But in general, that's kind of how we think they form. Dwarf galaxies is a very general term that covers a huge range in different sort of stellar masses or amount of stars in a system. And that means we can have several different types of dwarf galaxies. So at the very faintest end, we have what we call the ultra-faint dwarf galaxies. And these are the kind of galaxies that we think might have formed all their stars very early on and then had their star formation shut down early on. And then up from that, you have dwarf spheroidal galaxies, which are a lot like ultra-faints, but slightly more massive. So they might be able to sustain star formation for longer. And then as you go up again, you might have things like dwarf ellipticals or dwarf irregulars, which are higher mass. They'll have a higher number of stars. And then depending on the environment they live in, they can either continue forming stars like dwarf irregulars do, so things like the Large and Small Magellanic Cloud, or they maybe fall into a really massive galaxy and have all their gas stripped away, and so then they stop forming stars and they have a more elliptical kind of shape, like massive elliptical galaxies. I think dwarf galaxies can inform us a lot about two main things. So one is potentially what is the nature of dark matter. So one of the cool things about these galaxies is because they have so few stars, even in their very centers, we can treat them as sort of tracers of the underlying dark matter potential, which you can't do in more massive galaxies because there's so many stars, there's gas, there's dust, and it's really hard to disentangle what's causing motion from the ordinary matter versus the dark matter. But in dwarf galaxies, that doesn't, or in the dwarf spheroidals, for example, that doesn't happen. So you can get a really strong constraint on how much dark matter there is right at the center of the galaxy. And different dark matter models make different predictions for that. So by understanding how dark matter is distributed in the center of these dwarf galaxies, we can then sort of try and rule out or rule in different models for the dark matter particle itself. And it's a bit more complicated than that because we also have to consider some other processes like star formation. But we think it can give us if we understand all that well, we can put a strong constraint on what dark matter is. And then by learning about all that star formation physics as well, in order to understand the dark matter, we're also placing really strong constraints on how stars form in the early universe and how these galaxies evolve over billions of years and how important feedback from star formation is in general. And I think that's another really interesting thing they can inform us about. So the type of data we have right now for dwarf galaxies spans a few different methods, I would say. So we have imaging of nearby dwarf galaxies just from wide field surveys like the Sloan Digital Sky Survey and Dark Energy Survey, from which you can work out things like the brightness and the size of these dwarfs and how far away they are. We can use things like the Hubble Space Telescope and JWST to measure the star formation histories of these objects to see how they've built up their stellar mass over the whole history of the universe. And using Gaia for nearby dwarf galaxies, we can also work out how they're moving in 3D around the Milky Way, and potentially also how the stars are moving in 3D within the dwarf galaxies, which is something we haven't been able to really do before. So that's really interesting. And I think in the future, what we're really excited about are telescopes like the Vera Rubin Observatory, which is doing this large-scale survey, which should find many more of these extremely faint dwarf galaxies, not just in the Milky Way, but further afield. And the number of faint galaxies that we expect to find changes based on our cosmological model. So that just finding them or not finding them will give us some really interesting insights over the next 10 years as the Vera Rubin Observatory runs its survey. Also, we have spectroscopic observations of individual stars in nearby dwarf galaxies, and these are really interesting for trying to constrain the nature of dark matter and also for getting chemistries of stars. And there are a lot of surveys coming online in the next few years that will do this for far higher numbers of stars than we've been able to do in the past. So things like WEAVE and Foremost and MOONS, all of these are kind of these wide field surveys that are able to take spectra for many, many stars at one time and should hopefully really build up the data sets we have for dwarf galaxies in the nearby universe. If you have any questions about what I've talked about today or just want to discuss dwarf galaxies in general, you can find me on Twitter at Michelle_LMC.